class. Today we're going to be working on section 9.1, which begins hypothesis testing. And this part of the class is my favorite part of the class. What I like about it is it's going to take a lot of the little things that we've learned and bring them together into a process that combines a lot of concepts so that we can apply it. We will be working on this from this point in the semester all the way to the end of the semester. So it is really important. Initially, when you start this process, when you start to learn about hypothesis testing, it's going to be a little tricky. A lot of times what I hear from students is, I can do the problems or I can do the steps, but I don't really get what I'm doing. And that's really normal to feel that at the beginning. You're going to get really comfortable with this, especially if you're practicing the problems online and you're doing the homework and you're coming to see me if you need help. We're going to learn part of the process today. So the goal today, I'll give you a big picture of what hypothesis testing is. We'll learn how to do the first step in the hypothesis testing procedure, which is writing the null and the alternative hypothesis statements. So that's our goal for today. We will take some notes. I have a little activity we're going to do that will give you a big picture of what's going on, and then we'll work on writing those null and alternative hypothesis statements. So let me get the notes up. So as you can see, I have the notes sheet pulled up for section 9.1. You should have that out taking notes as you're viewing the video. We will not be using the calculator today. We'll get into that when we get to section 9.5. So you can see in section 9.1, it's called null and alternative hypotheses. And when you look at that word hypotheses, that is the plural of hypothesis. So we're going to be writing hypothesis statements. Plural of that is hypotheses. So a hypothesis you've probably heard of before. In science, a lot of times we talk about a hypothesis being an educated guess. For statistics, we're going to be a little more specific with our term hypothesis. And the hypothesis is going to be a claim or statement about some feature of the population. And by that feature of the population, I mean, maybe it's a population mean, maybe it's a population proportion, maybe it's a population standard deviation. So each section will focus on a different population parameter. The ones we're going to look at in this chapter will specifically talk about proportions and means. So all of the claims that we do will be for proportions and means, and we'll be talking about one sample. The idea with a hypothesis test is that it is a procedure. It's a process, a step-by-step process that we follow to test some kind of claim about a population. I usually refer to hypothesis tests as hypothesis tests. They can also be called tests of significance or tests of inference. You're inferring something from your data. So here, what I want you to keep in mind, we're always looking at what is happening in the sample, and then we're extending the results to the population. So just like in the last chapter, when we were talking about confidence intervals, we looked at what's going on with the sample, and then we extended those results to the population. That is our goal with hypothesis testing as well. It's just a different way to do that. Okay, taking a look at some examples of claims. I'd like you to see that hypothesis tests can be done in any area. lots of different areas, lots of different majors. You can have a claim or a hypothesis test really about anything. So some examples of claims. First one, the Genetics and IVF Institute claims that its XSort method allows couples to increase the probability of having a baby girl. So their claim is that their method allows them to increase the probability of having a baby girl. We would look at the data, we would see, is their claim supported by the data or not? Second one, a newspaper headline makes the claim that most workers get jobs through networking. So we would have a study where we examined that claim. We would have a sample, we would check with people, okay, how did you get your job? Was it through networking? Was it through another method? And then we would look at the results and decide, do we support this claim or not? The third one, medical researchers claim that when people with, that should say colds, colds are treated with echinacea, the treatment has no effect. So this would be a medical study. We would probably have an experiment where you had a group that had echinacea and a group that did not, similar to that one problem that we did, gosh, when was that? Back in chapter 3, I think, 2 or 3. We would look at our sample data, and then we would decide using statistics and the methods we're going to learn in this chapter, whether we support the claim or not. Okay. I want to talk to you a little bit about the big picture with hypothesis testing. So I'm just going to put big picture here. And the reason the big picture is so important, a lot of times when you're working with hypothesis testing, there's going to be some new terms, there's going to be several steps, and it's easy to get lost in the process and forget the whole goal. And I really like this activity as a way to help you visualize. It's a way for you to step back and look at the big picture of hypothesis testing without worrying about all the little tiny details. And this activity was designed by one of my colleagues, Lois Yamakoshi, who has since retired. Gosh, I've probably been teaching statistics over 10 years. And the first time I was going to teach it, she said, would you like to come observe my class? And hypothesis testing would be a good lesson for you to see me do. And she used this lesson in her class. And according to her, when she taught hypothesis testing, she used to have to teach it twice. When she started using this activity, it helped students to understand the big picture of what was going on. So if we were in class, we would be doing this activity. So I'm going to show it to you. I'm going to model this situation. So it's an M&M's example. Our claim, and we could say this is the claim of the M&M's Mars company, and their claim is each bag is 16.5 grams. The weight of the bag is 16.5 grams. We're going to take a sample of these bags of M&Ms, and we're going to decide, do we fail to reject their claim? Okay. Do we say we agree that there are 16.5 grams? Or are we going to reject their claim? And we'll talk about the logistics of this later on with our conclusions. But for right now, we're just saying, okay, do we agree? Yes, each bag is 16.5 grams. So let's just do this. Agree that they're 16.5 grams. Or do we disagree? They're different than 16.5 grams. And by different, I'm not talking about a little bit different. I'm talking about, are they significant? Let me fix that guy. Are they significantly different? because you're going to see in a second, I have peanut M&Ms. Well, because of the peanuts, they don't all weigh exactly the same. But we're going to say, are they about the same, or is there a significant difference? I'm going to pause for a sec and go back to the video so that you can see the activity. And again, the idea here is there a significant difference? Okay, as I said, we're going to look at a sample of fun size M&Ms. And what I did is I poured them in this bowl. And what I'm going to do is just mix them up a little bit. Kind of makes you think of probability, right? So here's my sample. And what we're going to do is we're going to pull out one of these fun size M&M samples. And we're going to say, okay, does this weigh, what did we say, 16.5 grams? Now, if I had a scale, I would be weighing this. I don't have a scale. So I'm just going to use this as my main one. And I'm going to say, okay, does this one feel about the same? It seems accurate. It's about 16.5 grams. So I say, okay, yeah, that one looks good. So again, I'm going to mix this up. I'm going to pull another one out. Again, if I had a scale, I'd weigh this. Does this seem like it's about 16.5 grams, about the same? Or is there a significant difference? Feels like it's about the same. And we would go through with our sample and we would continue to measure, to weigh, to determine, okay, do we agree that the weight is 16.5 grams? Or is there a significant difference? Okay. Pull out one here. And the next one I get out is not the same as 16.5 grams. This one looks a little heavier, wouldn't you say? So this one I would say is a little bit more, maybe double or triple. So it's significantly different. It's significantly more. Okay. So again, I'm going to be picking these guys up. The next one I'm going to grab out. Okay, that one looks about the same. And I'm going to continue going. And then I get this one. And I don't know if you can tell, but this one is empty. It doesn't weigh 16.5 grams. It weighs nothing. So this one would be significantly different than our original. This one would not weigh 16.5 grams. It would be significantly less. And you think about it, this happens sometimes. I mean, I think you've had that happen where you get that pack and it's got like 1 in there or 2 in there. So you feel like you got gypped. So from the M&M's Mars company, they're claiming, hey, this is 16.5 grams. This one is significantly lower. So we would continue with our sample and we would keep testing. Are they about the same? Is there a significant difference? Look at this guy. Quite a significant difference. You'd be happy if this showed up in your bag of fun size M&Ms. But again, we're just checking, is their claim correct? Do we support their claim? Well, this is significantly higher, quite a bit significantly higher than the 16.5 grams. And again, we would continue and we would keep track. Are these about the same? Is there a significant difference? So again, this one would be significantly higher. Maybe not to the point of this one, but they're definitely not 16.5 grams. And from a big picture standpoint, this is what we're looking at with hypothesis testing. We're looking at when we take that sample, confirming, is this claim correct? Do we agree with this claim? Or is there information, is there data that shows us something else is happening, that there's a significant difference, not a little bit of a difference, a significant difference. Okay, I wish I could share some of these M&Ms with you. I'm probably better off not having them. Good thing Halloween's coming. Let me pause the recording and then we'll go back to the notes and I'm going to summarize what we did in the notes. So we're back to our notes and I just want to highlight what we did in your notes so that you can see how it's going to tie into our hypothesis testing. So we're going to start with the assumption that our population is normally distributed, or we can also assume that we have a large enough sample size, over 30, so that our means would be normally distributed. So what we were looking at is we were saying, okay, the average weight, the weight is 16.5 grams. That's what we were looking at. And then as we looked at our sample and we took out the individual bags and weighed them or compared them, we had some that might have been like about the same or maybe a little bit higher or lower. And then we had a couple that were quite significantly larger. And then we had one that was empty, that was significantly lower. So when we get to the point that we're analyzing our sample and looking at our sample data here, we would look at, okay, is it in the middle here? Is it close to that mean? Or is it significantly higher or significantly lower? And when you look at that, it kind of looks like a confidence interval a little bit, right? The middle is are the values that are close to the mean that we're talking about. Over here, these values would be significantly high, and these values would be significantly low. And again, probably each bag is not exactly 16.5 grams. There's probably some that are a little bit more and a little bit less. We're not talking about a little bit of a difference. We're talking about a significant difference, a lot higher or a lot lower. And that's going to be something key that I want you to keep in mind as we move forward. All right, so we're moving forward here. This is the process or the procedure that we're going to use for hypothesis testing. As we're working on this, you're going to see this in your notes for this section, for the next section, and for the third section. You're going to see it all week for every set of notes. So you're going to get really familiar with this. Today, for section 9.1, we're going to learn how to write the null hypothesis and the alternative hypothesis. That's the HO and the H1 with the claim indicated. So we're going to learn that today. These two steps right here, we're going to learn in section 9.5. So we're going to learn that later this week. 9.5, finding the test statistic and its p-value. Right now, you're probably going, what are those? You will learn them. We will learn them in section 9.5 on Wednesday. The p-value, comparing it to alpha, all that is going to be learned on Wednesday. And then section 9.4 is writing the conclusion or the answer to the question. And I could also put claim here. I might like that. Responding to the claim in non-technical terms. Okay. So really, the first step and the last step, there are going to be some symbols but there's not a lot of number crunching. It's more getting going with the problem and finishing off the problem. The middle steps, that's where the numbers come in and the statistical analysis comes in. The introduction and the conclusion are very important, but it's not so much the number part of it. Okay, so let's talk about step one. So in step one, we're going to learn how to go from the wording of the claim to writing it in math symbols. And we have two different hypothesis statements we're going to make. The first one we're going to write in symbols is called the null hypothesis, which is H, we say H sub 0. That's what we're starting with. And the null hypothesis will always have an equal sign in some form. And sometimes that gets people. So let me show you. This one is the straightforward equal. That one's not so bad. Here, this is a less than or equal to symbol. It does have the equal in it, so it would still be considered in the null hypothesis. And this one is a greater than or equal to. So when we start working on these, as we write our null hypothesis, we're going to ask ourselves, is there an equal in here anyway? If there is, we write that statement or we write those symbols in the null hypothesis. The next one we're going to look at is called the alternative hypothesis. You'll notice here it says H sub 1 or H sub A. I typically use the H sub 1, and many books use that. H sub A can also be used. So you can see those used interchangeably. I'm going to emphasize the H sub 1. H sub A just means alternative hypothesis. The 0 and the 1 just means either this is happening or this is happening. You either have this statement or this statement. And it's essentially the complement of what you have in your null hypothesis. So if you have an equal in the null, you'll have a not equal in the alternative hypothesis. If you have less than or equal, you will have greater than. If something is not less than or equal, it is greater than. If you have greater than or equal to, you will have less than. So what you're doing in the alternative hypothesis is having the complement. So the HO and the H1, the null and the alternative, are complements. In this section, the hypothesis statements, let me just highlight that, will be about a proportion or a mean. And like I said, we're going to be doing hypothesis testing till the end of the class. So you're going to get really good with hypothesis testing. For now, in this chapter, we're going to start with proportions and means. And again, you see a mu here because we're looking at the sample and making a statement. We're extending it to the population. So our conclusion is about the population. You'll also notice we did chapter 8. Getting used to the new book. Chapter 8 had confidence intervals. Well, confidence intervals, we did proportions and means. So you're going to find for our hypothesis testing, we're doing proportions and means. Okay, we're almost ready to do some practice. I want to talk about what the critical region is. And the critical region is all the values that will cause us to reject the null hypothesis. The way we find the critical region is to look at the alternative hypothesis. And you know, let me write this in. This is HO, null hypothesis. Alternative hypothesis would be your H1 or your HA. And the critical region is cut off by your critical value. And we know critical values, right? We've done the Z alpha over 2, and we've also talked about the T critical values from the table. Okay, so let me show you what a critical region would look like. So let's say we had an alternative hypothesis that said the proportion is greater than 0.5. What we're looking at is this symbol, greater than. When we look at our normal distribution, we would think of the 0.5 being here. If we find something that's significantly greater, so let me put significantly greater than the 0.5, where would it be in this picture? Well, the values that are greater would be up here. This is called your critical region. So if we found that something called our test statistic is in this region, we would say, okay, we do think that the proportion is significantly greater than 0.5. What you'll notice here, you could get a cutoff for that region, a cutoff value. That is your critical value. The critical value cuts off the critical region. And you might say, well, how far is far enough? Kind of like outliers. Well, how far does it have to be considered far enough? You will be given a level of significance, and that will typically be tied with a 5% or a 10% or a 1%. So it'll be similar to the 90, 95, and 99 we use for confidence intervals. The important thing right now is that if you see a greater than, you can identify that the critical region is the highest part to the right. If we had a less than, let's say we had less than 0.5. Gotta draw my picture smaller so I can make it fit. Well, where are the values significantly less than 0.5? They'd be down here. So that would be the critical region. And this would be your cutoff. And then the last one, let's do a not equal. So again, if we looked at a normal distribution, if it's significantly different than 0.5, if it's not equal to 0.5, it could be a lot higher than 0.5 or a lot lower than 0.5. So your critical region is these two together, the shaded part. And the cutoff, again, the critical values would be there and there. When we look at these pictures, you'll notice this picture here has one critical region. This is called right-tailed. in terms of the hypothesis test. This one's called left-tailed. And this one, it has two tails with the not equal, so we call it a two-tailed test. And we're going to build on that. Again, it's a lot of new materials. We're taking it step by step. All right, so we're going to move to some examples. And right now, if you're feeling like I've given you a lot of information, that would be a normal feeling. I would expect you right now to be like, okay, I'm not quite sure where she's going with this. Again, our goal is to be able to write the correct null and alternative hypothesis statements. So we're writing the HO and the H1. We're going to indicate the claim. So we're going to say which one's the claim. And then we're going to draw a picture shading the critical region. And that's all we're doing right now. When you're finished with this example, you're probably going to feel a lot more comfortable with this. So the key things as we're doing these, we're writing HO and H1. And the key thing I would want you to remember, if we go back here, we said right here for the null hypothesis, it always has an equal somewhere in there. Equal, less than or equal, greater than or equal. The alternative hypothesis will not have an equal sign. So it could be not equal, and you might say, well, that's an equal sign. It's not equal, though. Greater than, less than. So these three symbols you'll see in the HO. These three symbols you'll see in the HA or the H1. So here's how I do this. We're going to look at these examples. Let's look at what the claim says. So the claim on this one says, test the claim that the average cost of a used car is less than $10,000. Now, I see the word average. Again, we're talking about figuring out something about our population. So the average is less than 10,000. And again, if you know you have some problems with the less than and the greater than sign, talk to me because I can give you some little hints with that. When I look at this, does it have an equal? No. So it goes in the H1, in the alternative hypothesis. I started to write equal. That's not good. The other thing that I think will help, write the word claim here. Some instructors just put a C, somehow have a way to remind yourself that that's the claim. That's going to help when we start writing our conclusions. If this symbol is less than, if it's not less than, what would be left? The complement of less than. Well, it could be greater than, or it could be equal to. And you keep that same number in there. That would be our hypothesis statements written. Okay, so we either have greater than or equal to or less than. One of these two options is happening. When we do our hypothesis test, we'll be figuring out, well, do we think HO is happening or do we think H1 is happening? We're basically making a decision between the two. Now, we want to draw a picture shading the critical region. And when we go to shade this, sometimes looking at this like the way it is now can be kind of tricky. So what we typically do, we've gotten this all written. We put, and let me get a different color here. We put just a straight equal sign up here. And you'll notice that when you go to the My Open Math, you can really use either symbol, greater than or equal to or less than equal to, because, greater than or equal to, because everything that we're going to be looking at from this point on is going to have to do with H1. It is probably to your benefit to write just a straight equals in there. Either one is okay. The reason I would suggest maybe writing just the equal in the middle, when you go to draw your critical region, you have an equal, you have a less than. Okay, we're doing a less than. Significantly less than. The values that are significantly lower are on the left side. It's a one-tailed test. It's the left tail. Okay. When you draw that picture, it's always from H1. That's what your picture's from, your alternative hypothesis. Again, if you want this, if you want to keep it greater than or equal to, some students like that better because it helps them realize, okay, it's either greater than or equal to or less than. So you've got everything exposed. You got everything covered. You're going to see that equal. And so a lot of times in my classes, at least, students start off writing the greater than or equal to, and then slowly they morph into being comfortable writing the equal. I will accept either. You will see the equal on my open math. Okay, let's look at another example. This one says, test the claim that the mean number of hours that a college student studies per week is not 10. Is not equal to 10. And can you see that this is a mean? It has that word in there, so it makes it a little easier. The mean is not equal to 10. Does it have an equal sign? Not really. It says not equal. So we know anything that does not have equals goes down here. And that is our claim. So write the word claim there. If we're not talking about not equal, the complement of that is equal. Again, to draw our critical region, we have our normal distribution. I would think of equal to 10 in the middle. If it's not equal to 10, it could be higher or it could be lower. You have two sections for your critical region. It's a two-tailed test. And again, these are your critical regions, that shaded part. Okay, next example. Test the claim. And you notice that the claims kind of announce themselves. That helps a little bit. Test the claim that college students spend 25% of their income on entertainment. Okay. This one sometimes students have a harder time with. You don't see a greater than, you don't see a less than. College students spend 25%, equal to 25%. So our proportion here is equal to 25%. Now, whenever we have a percentage, we always want to write it as a decimal. So you're going to say the proportion is equal to 0.25. Make sure you write it with the decimal. And I actually looked at the MyOpenMath, and they write it with the percentage. I think you're better off writing it with the decimal. I want you to write it with the decimal because also when you enter it in the calculator, when we get to steps 2 and 3, it's going to be better if you have it with the 0.25. This is our claim. And this is the first one when the claim is up here. And we'll talk about the advantages and disadvantages of where your claim is in the next sections. So if you had an equal up here, what would you have down here? I hope you said a not equal. Again, these are complements. Either this is happening or this is happening. And when we have the data from our sample or the statistics from our sample, we'll be able to analyze that in the sections coming. We're going to draw our critical region or critical regions. Again, you're drawing it based on H1 because it's a not equal. It could be significantly lower or significantly higher. Next one. This one gets students sometimes. Test the claim that the majority of the class earned a passing grade on the last test, which I do think was the case. The majority. So I want you to think about something. If I had you reply to something and I said, okay, majority wins, would you rather do your project in one part or two parts? What would the majority mean? Majority is most. Majority is over half. That would be the majority of our class. So the proportion is over half would be majority. That's over 0.5. You could also think of it as over 50%, but you're going to have to convert it to a decimal anyway. So the claim is over 0.5, greater than. Greater than does not have an equal in there, so it goes in the alternative hypothesis. And this is our claim. Up here, again, if it's not greater than, it would be less than or equal to 0.5. Now, if you want, you can leave it like that. Or, as I said, a lot of the time we just put a straight equals there. Critical region, greater than 0.5. Well, where are the values greater? They're over here. So this is a right-tailed test. All right, last one. Test the claim that the mean age of LMC students is greater than or equal to 20. Mean, I think you see that, there's our mu, greater than or equal to, greater than or equal to 20. It has an equal in there, so it goes in the null hypothesis, and this is our claim. This one is greater than or equal to. If it's not greater than and not equal to, we would have less than. And again, you can change this to an equal. That's fine. What's going to be important is this symbol for our critical region moving forward. The less than values, significantly less than 20, would be over here. This is a left-tailed test. Okay, so we've gone through several examples. You notice I did some means and some proportions so that you could practice writing the null and the alternative hypothesis. It's important to get this part down because what you write for the null and the alternative hypothesis statements is going to determine which formula or which calculator function you use to perform the hypothesis test. So getting these right to begin with is critical for the rest of it. It's the beginning of the problem, so that's going to be really critical. In the next section is what, 9.4, I think, yes. So we can skip a couple sections. 9.4, we're going to learn about step 4, which is writing the conclusions. So at this point, you can begin working on your MyOpenMath. For section 9.1, you'll have additional practice with writing the hypothesis statements. Have a good rest of your day.